Hello, algebra students. Just a minute, let me close my door. Okay, so I wanted to do a video about graphing exponential functions. We just talked about functions in class today. So, for example, y equals, I think we did in one class, was like 2 times 1/2 to the x. So this is a function, so we could write it as f of x equals 2 times 1/2 to the x. Remember, for order of operations, you would do the power first, or the exponent first, so that means you would take care of this action first. Then when you're done, you'd multiply by 2. So if we were to draw a little function machine, this says the first thing is to put 1/2 as the base, and the number goes right there. And then the second thing is to multiply by 2. So that's what happens. This is, again, we talked about in class that this is kind of a weird operation, that you're taking your number. Where are you plugging your number in? You're plugging it into the exponent of 1/2. In this function, the base is always 1/2. So in an exponential expression like this, 1/2 to the x, we call that the base, right? We call that the exponent. We did power functions before, like y equals x squared. In this one, the base is an exponent. I'm sorry, the base is a variable, and the exponent is a number. So remember, we did parabolas. When we graphed these things over here, they were parabolas, and we just graphed some of these guys over here in class today. So they behave very differently. When the base is a variable and the number is an exponent, we call that a power function, and polynomials are examples of this. In this case, the base is a number and the exponent is a variable. We call that an exponential function. And exponential functions are what we're talking about for the next 2 weeks. As I said in class, exponential functions are very, very applicable, because a lot of things in life grow exponentially. Okay? All right. So if I drop, for example, I think in class today we dropped in like a 0. Of course, 1/2 to the 0 power is 1. Multiply that by 2 and you get out of 2. So today we created these little charts where this is x, this is f of x. Drop in a 0, get out of 2. If I drop in a 1, 1/2 to the first power is 1/2. 1/2 times 2 is 1. So got a 1. And we noticed, after we did a few of these, there's a pattern. Drop in a 2, I get 1/2. Drop in a 3, I get 1/4. Drop in a 4, I get 1/8, etc. And if we went the other way, drop in a -1. 1/2 to the -1 would be 2, because remember, 1/2 to the -1 is equal to 2 to the first, because the negative exponent means flip it over. And then 2 times 2 would be 4. So I'm dropping a -1, I get a 4. If I drop in a -2, I get an 8. Drop in a -3, I get a 16. And so then when we graphed it, we saw that at 0 it was 2, at 1 it was 1, at 2 it was a 1/2. But if we go the other way, at -1 it was 4, at -2 it was 8, way up there. So we discovered that it looks kind of like this. And we talked about that this the right side is coming down to a horizontal asymptote. Yay. Which is a line that the graph gets closer and closer to and never crosses. Okay? So let's look a little bit more closely at this. So notice that in my equation, it's f of x equals 2 times 1/2 to the x. Notice that this crosses the y-axis at 2. And notice that there's a 2 right here. I find that interesting. Let's see if that's just a quinkydink or a coincidence, or if it actually is telling us something. So remember, the other one we did in class was f of x equals 2 times 2 to the x. If you remember in class, we graphed that thing. We found out that it looked like this. Kind of like the first one on the flip around. So notice that this one also crosses at 2. And that is also 2. So to see a pattern, let's hop over to Desmos, because Desmos is really helpful for seeing patterns. And let's graph a bunch of exponential equations. So let's do like 3 times 0.5 to the x. And let's do 3 times 2 to the x. Interesting. Notice that it crosses at 3. And we have a 3 there and a 3 there. Let's try something completely radical. How if I do a 4 times 1.56 to the x? Oh, look at that. It crosses at a 4. So it doesn't seem to matter what's inside the parentheses, what the base is, but this number out front seems to tell me where it crosses the y-axis. That's very interesting. If you remember, let's get rid of one of these. If you remember when we did y equals, like, say 3x plus 2, going back to a linear equation, notice this number here is the y-intercept. You remember that from linear equations? That number is the y-intercept. And so what we're recognizing here is the y-intercept. You can see the y-intercept in an exponential equation. It's just the number out front, not the base of the exponent of the exponential part, but the number that's being multiplied out front. Okay? So let's do another one, like 4. I don't want you to see the graph yet. Let's do 4 times 3 to the x. Oh, you can see it. Shoot. I can't hide the graph. I figured out how to hide the graph. Oh well. So notice once again, here's 4 times 3 to the x. It crosses at 4. Okay, so let's switch back over to this thing. So let's say if I gave you a bunch of exponential equations like y equals 2 times 1/2 to the x, that's the one we gave you already, or y equals 4 times 2/3 to the x, or y equals 5/4 times 2 to the x. So what we're suggesting is that you can look at an equation like this, and before you hardly even think, you can tell what the y-intercept is going to be. So in this case, the y-intercept would be 2. Here the y-intercept would be 4. And here the y-intercept would be 5/4. Okay? So in an exponential equation, in general, it looks like this. we're gonna say that the A is the y-intercept, or another way to say it is it's the initial value or the starting value. Now this is I think this is easy to understand, because remember the way we talked about exponentials in class is that exponential growth means you start somewhere and you grow by multiplying over and over again by the same thing. So notice in this, the way this is set up, that clearly I'm starting with A and then multiplying over and over again by B. So it makes sense that A would be the initial value, or the value that I get when I plug in 0 for x, which is the y-intercept, right? So in general, we can say that A is the starting value or the initial value, and B is the thing that I'm multiplying over and over again by. So we're going to call that the growth factor. Okay? So let's go back to Desmos and do some more investigating. So I'm going to close all these out, and I'm going to just throw some functions up here real quick. And let's say 0.5 times 2 to the x, and let's say 3.2 times 2 to the x. Okay, so notice that no matter what we do, it doesn't matter. Notice I'm keeping the growth factor the same. So there is 3.2 because that's the green one. Notice the red one crosses that. No, the red one. Quiet for a minute so I can do this. Yeah, so the red one crosses at 3. And notice that the blue one crosses at 0.5. So you can see clearly that the number that's being multiplied out front is the y-intercept. Okay, now what if we look at, instead, let's make all of our y-intercepts the same, make them all cross at 2, because we're going to investigate how the growth factor affects the graph. So you notice they're all crossing at 2, and they all have a growth factor of 2, so they're of course on top of each other. So what happens if I take this and put a 3 there, leave that one at 2, and put a 1.5 there? Okay, so notice that before the y-intercept, the red's on the bottom, and after the y-intercept, the red's on top. The red's bigger, right? So what happens when I increase the growth factor? It's not a surprise. The graph grows faster after the y-axis, but it's underneath. It's less before the y-intercept. So in other words, from this point, it grows faster and diminishes faster, right? So because here I'm going backwards, there I'm going forward. So both of these show a faster growth rate. So I come in here and suddenly it just takes off, right? So that's interesting. So the bigger the growth factor, the faster my graph is going to grow, which again is not surprising. If it's a growth factor, then we would think bigger numbers cause it to grow faster. But notice all of these graphs are increasing. Right? We talked about in the class today, increase means that as you go from left to right, the y's are getting bigger. And that's true of all of these, right? As I go from left to right, the y values are getting bigger. Now, what happens if I put, instead of 1.5, I put a 0.5 there? Whoa, look at that, it switched. Because if I'm multiplying by 0.5 over and over again, then my graph is going to decrease. My numbers are going to get smaller, right? If I start at 2 and multiply by 0.5, I get 1. Right? If I start at 2 and multiply by 2, I get 4. So if I'm multiplying by a number bigger than 1, my graph is going to grow. If my growth factor is less than 1, then my graph is going to decrease. Okay? So, let's hop back over here and make the conclusion of this. So the y-intercept tells me where it crosses, or the a tells me where it crosses the y-intercept, and the b tells me how fast the y values are growing, and the function is increasing if the b is greater than 1, and it's decreasing if the b is less than 1. Okay? So that's my spiel about graphing an exponential equation. I'm going to say one other thing. There's a special number. You guys are all familiar with pi, right? You know that pi is approximately 3.14. We have another special number called e. E is approximately 2.71. And you're going to see e shows up a lot in exponential discussions. So if you see an equation like f of x equals e to the x, don't get alarmed. That e is a number. In fact, we can hop back over to this and graph it real quick. Let's close that, and close that. If we type in e to the x, notice it grows, and notice that it crosses at 1 because we just have 1 out front. But notice as we go to the right, from here to there, oh, that's 0.5. I want to go to 1 right there. Notice that's approximately 2.71 because that's what e is, right? I multiplied. If I go over 1, I'm going to go up approximately e, which is 2.71. Let's go over a little bit. I need to hit on 1. I did it quite at 1. Oh, here, let's just put in this. X equals 1. There we go. Now we have a point there. So notice that point is 1 comma 2.718 because that's what e is. E is 2.718, etc., etc. It's an irrational number, so it goes never-ending, non-repeating. So that's just alert you because some of your problems will have an e in it, and it's not a variable, it's actually a number, just like pi is a number. Okay, hopefully this is helpful, and have fun working on this stuff.